Hello everyone, I'm SIR-model a math cat, that weird species in love with numbers and theorems. Today we are going to see how maths can help us save lives in this deadly COVID-19 pandemic. Let's begin. Let's model an epidemic with a simple mathematical system. It consists of a box and few dots in it. Every dot is given a random position and a random velocity. And then we let the laws of physics evolve the system. Every collision in this system is elastic. Therefore, the system does not lose any energy and can potentially go on forever. A collision between two dots represents an interaction between two people. Two people might have met, shaken hands, or come in close contact with each other. The way an epidemic like COVID-19 spreads is through human-to-human transmission. This means that if two people interact, it's possible for an infected person to pass on the infection to an uninfected person. To study a pandemic, we will color code our dots. The gray dots represent people who are not infected by any virus. So they are people who are susceptible to being infected. The orange dots will represent the people who are infected with the coronavirus. However, these are people who do not show any symptoms. So these are asymptomatic people. The red dots will represent the people who have been infected by the virus and are showing symptoms. Finally, the green dots. The green dots represent those people who have recovered from the COVID-19. The state of a typical particle in our animation will progress as follows. Initially, the dot would be gray. That means the person is not infected but susceptible. Once they collide with either a red or an orange dot, they will change their color to orange, meaning they have been infected by the virus, however, they're not showing symptoms. After that, after a random amount of time, the orange dot will change its color spontaneously to red, showing that the person has now developed symptoms. Then, after a random amount of time, the red dot will turn into green, showing the fact that the patient has recovered. Every time two people interact, it's not the case that an infected person passes on the virus to an uninfected person. Therefore, when an orange dot collides with a gray dot, we will change the color of the gray dot to orange with probability 1/2. This makes our system stochastic. What this means is that if there are a large number of collisions between orange dots and gray dots, the gray dots will change to orange about half the time. Recall that the red dots are also people who are infected by the coronavirus. When they collide with the gray dots, we will change the color of the gray dots to orange with probability 1/2 also. Let's introduce another tool that will help us study an epidemic, the infection tree. In this tree, we keep track of who infected whom. We also keep track of when people got infected. Thus, when we run an animation or a simulation at the end, we can look at this tree and try to extract some information from it. At the end of our animations, we will look at the infection tree. However, we will redraw it. On the x-axis, we will place time. Thus, if a person got infected early, they would appear before a person who got infected later. The y-axis would not be representing anything, and we will use scientific license to make our tree look nicer. With this color coding, let's get back to our colliding dots animation. Here is our patient 0. As we start the animation, we see that the infection is passed on to other people. Here, the tree is keeping track of who is infecting whom. This tree is a bit of a distraction, so we will turn it off for now. We'll get back to it at the end. The coronavirus starts spreading throughout the population, and pretty soon, some people start to develop symptoms. As time passes, the number of infected people increases. However, some people start recovering from their illness. Let us stop our animation and at this point introduce a tool to study our epidemic, the bar. The bar keeps the counts for us. First, it counts the number of red dots representing the infected people who are showing symptoms. After that, it keeps a count of the orange dots representing the asymptomatic infected people. Then it keeps a count of the gray dots representing the number of people who are susceptible. And finally, it keeps a count of the green dots, the people that have recovered from their illness. Let's restart our animation. The bar now shows what's happening in our colliding dots animation. It gives us a summary of what is going on in the epidemic. At this point, we introduce the most important tool used by epidemiologists to study an epidemic, the curve. The curve records the status of the bar over time. On the x-axis, we have time, and on the y-axis, we have the status of the bar. If we look at the curve, it's quite jagged. This is fine as the bar records the number of people, which is always an integer. So the values of the bar jump from one integer to another. For aesthetic reasons, we replace the jagged curves with smooth ones. To do this, we have to use curves that approximate the exact values of the bar. Using these approximate curves is not a problem, as we can always go back to the exact values of the bar whenever we need more accurate information. As we restart the animation, we see that the bar and the curve nicely summarize what is going on in the epidemic. Since many people have been infected and many of them have recovered and have become immune to the virus, the epidemic starts subsiding. More and more people are recovering. And soon the epidemic ends. At this point, we can stop our animation and look at our curve. When we look at the curve, the most important and prominent feature in the curve is what is called the peak. That is the time when maximum number of people are infected. What we would like to know about the peak is when it happens. That is shown on the x-axis. As the x-axis is the time, therefore the point where the peak happens on the x-axis is when the peak happens. The y-axis tells us how many people are affected by it. Since in our animation we have separated out the symptomatic and the asymptomatic people, we actually have two peaks. We should be more concerned about the peak in the red color, as these are the people who are symptomatic and therefore need health care. Let's go back to our animation and recall that we were keeping track of who was infecting whom. This information was summarized in the infection tree. Let's have a look at it. This tree is quite messy, so as we had said before, we are going to redraw it. Now, the x-axis represents time. So the first node is the root. What we can do is take a small slice of time and run it through the tree. All the dots that fall in this slice are the people who were infected during that time period. And counting those people can give us a lot of information. It tells us when the epidemic was at its worst. Let's discuss a very important quantity in epidemiology called the R value. What we can do is we can take a small slice of time and look at the dots that fall in it. The number of edges coming out of those dots are the number of people that were infected by that dot. The average taken over those dots is what is called the R value. As we move the time slice across the entire timeline, the R value changes and we can see that. Epidemiologists want this R value to be small. If the average value of this quantity is greater than 1, then the epidemic is spreading and the number of people getting infected is increasing. If this quantity is exactly 1, then the number of infected people stays the same. And when this drops below 1, the epidemic slowly dies down. So our goal is to reduce the value of R. So how can we reduce the value of R? We can do that by behaving in a socially responsible way. In our animation now we introduce double dots. These are people who behave in a socially responsible way. So what they do is they wash their hands often, they don't shake hands, they keep their distance from others. When they collide with other dots, then the probability of an infection being passed on will be dropped down from 1/2 to 1/4. This means that when people behave socially responsibly, the probability of the virus spreading reduces. Let's see what happens when we introduce these people in our animation. Let us look at what is the effect of people acting socially responsibly. In this animation, we have 50% people who are practicing socially responsible behavior. The rest of the 50% are just acting normally. As we start the animation, we realize that the epidemic does spread, but it spreads at a slower rate. The way we have set up this animation is the physics of this system is exactly the same as before. So the particles exactly start off at the same positions and they are exactly the same collisions that happened in the previous animation. So the physics of this system doesn't change. The epidemiology does. And the reason for that is the socially responsible people. Since their interactions have a smaller probability of passing on the infection, that has an effect of slowing down the growth of the epidemic. The number of infections does start increasing and finally starts to peak. This peak sustains itself for a little while, and after that, people start recovering. More people start recovering than the number of ones who are being infected, and the epidemic slowly goes away and the virus is under control. When we look at the last part of the animation, we realize that there's a large gray region in our bar and also in our curve. This means there were a lot of people who never got infected from the virus. If you look at the dots that are never infected, most of them are double dots. That actually tells us that people who practice socially responsible behavior are least likely to get infected. However, their behavior does also reflect on the other people, as there are some single gray dots which are never infected. So when 50% people behave socially responsibly, you can just look at the curve and see that it's flatter. It's interesting to look at the infection tree in this case. And what we realize is that this tree is longer and thinner. That means it takes longer for people to get infected. And at a given time, few people are infected. We can also estimate the R value over time, and we realize that it's much lower than in the previous case. In the next animation, we look at the scenario where 25% of the people are being socially responsible and another 25% people are being socially responsible and they're practicing social distancing. That means they interact with fewer people. Let's look at a person who's practicing social distancing. We have made this person static. What that means from a physics point of view is we have reduced the velocity of this particle to zero. Furthermore, we have given it infinite mass. Physicists will realize that that reduces the overall kinetic energy of the system, which means this system has a lower temperature. That means there are going to be fewer collisions, which translates to having fewer interaction. Now we can look at our curve. As we can see, this curve grows even more slowly than the previous one. And the peak happens after a long time. We are going to speed up the rest of this animation. The peak sustains itself for a little while. The number of people recovering exceeds the number of people who are being infected, and the epidemic starts to subside. Finally, the epidemic ends. We can once again look at the gray region in the bar. These are the people who are never infected. We realize that this region is even larger. This means a lot more people were spared by the virus. These people can be extremely helpful to those who have suffered from COVID-19. Let's also look at the infection tree for this animation. As we see, this tree is even longer and thinner. That means people get infected later, and at a given time, there are a few people who are infected. We can also observe the R value, which remains much lower than in the previous cases. It's instructive to look at all these three curves simultaneously. Let's first align their x-axes, and we realize that the peak happens earliest in the curve where people are just behaving normally. It happens later in the curve when half the people become socially responsible. And it happens even later in the curve when 25% of the people start socially distancing themselves. We can align the y-axis of these three curves and look at the peaks. We realize that the peak is highest in the first curve. And when people start behaving socially responsibly, it goes down. And it goes further down when people start socially distancing themselves. It's also interesting to look at the three trees simultaneously and observe the R values and see how they decrease as our behavior changes. In the next animation, we see the effect of having large gatherings during an epidemic. In this animation, we have divided up the system into four regions: the north, the east, the west, and the south. These regions are more or less isolated from each other. That is shown by the diagonal walls in the system. However, there are little slits in these walls. That means there is a limited amount of interaction between two regions. So the north does interact a little bit with the east and the west, and so on. The center of this box contains a place where people can congregate or gather. Initially, the epidemic starts in the north, and it starts spreading slowly. As you can see, the epidemic stays in the northern region until people decide to congregate in the middle. As soon as they meet with each other in the middle and mix together, the infection is passed on and a lot of people get infected in this large gathering. Once the gathering is over and people go to all 4 regions from it, the virus spreads like wildfire. Pretty soon, the curve peaks and many people are infected. We are going to speed up the rest of this animation. After a little while, the epidemic does start subsiding. However, that is happening because almost everybody is infected and people are simply recovering from their illness. This animation is clearly showing us that we must avoid large gatherings. Large gatherings are simply a recipe for disaster during a pandemic. Let us do an action replay and see how the virus spreads when we have this large gathering. Initially, one infected person gets inside the gathering. The first few interactions are lucky and the virus is not passed on. However, this luck soon runs out. Pretty soon, almost everybody inside the gathering is infected. A Pandora's box is created. And when the Pandora's box is opened, the infection is spread in the entire community. Let us look at the infection tree for this animation also. When we look at the tree, it becomes obvious when the large gathering happened and what happened after that. The R value shoots up and huge number of people get infected in a short amount of time. This animation is set up as before. However, in this animation, we do not allow people to have the large gathering. This animation is so long that we have to run it 50% faster. Let us look at the same animation and change something. This time, we do not allow people to gather in the middle. As we run the animation, we see that the epidemic spreads in the north. However, since people from the north are not really interacting with the other people, therefore it remains more or less confined to the north. After a while, the epidemic does start spreading to the east. And now people in the east start getting infected. And pretty soon we have a peak in our curve. People in the east and the north are infected, whereas the people in the south and west are spared. At some point, the epidemic does reach the people in the south. However, in this case, they happen to be lucky and it doesn't really take off and subsides. After a little while, the infection moves from the north to the west. One infected person from the west also reaches the south. And this time, the south is not so lucky and the epidemic takes off in the south. West and south are now being infected and we have another peak in our curve. After a little while, people start recovering there and the epidemic subsides. So in this particular case, we have 2 peaks in our curve. The first peak happened when people in the north and the east were being infected, and the second peak happened when the people in the west and the south were being infected. Let us look at the infection tree in this case. This tree is so much longer than before. We also notice in this tree that if a few infections wouldn't have been passed on, the second peak could have been avoided. This means that if people act at the right time, a large number of people can be saved from the epidemic. The coronavirus can not only spread from humans to humans, but it can also spread through objects. An infected person can touch an object like a doorknob and infect the doorknob. And later on, when an uninfected person touches the same doorknob, they can get infected by the virus. In this animation, we try to explore this aspect of the coronavirus. In this case, the infection is not only passed from humans to humans, but it is also passed on from humans to objects. These objects get infected and then they in turn start infecting people. As the animation goes on, the objects get more and more infected, which is reflected by their color turning redder and redder. Pretty soon, these objects also become a major contributing factor in the growth of the epidemic. After a little while, almost everybody in the population has been infected by the virus, and now people start recovering. This is only natural. Once everybody has been infected, there is nothing else that can happen other than people recovering. What is extremely interesting to look at is the infection tree for this animation. When we look at this tree, we realize that it's not a tree. It's what graph theorists call a forest. It's a collection of trees. The first tree is the one that was started by patient 0. The second tree was started by a person who got infected by an object. The third tree was started by another person who didn't directly get infected by a person but an object, and so on. So each tree in this forest is like an independent epidemic going on. In fact, there is a reported case where an infection was traced to a salt shaker. Our next animation is set up precisely in the way we did the previous animation. In this case, again, we have these infectables, which can be infected when infected people collide with them. However, in this case, we have these beautiful people who come and periodically clean these infectables. We can look at this animation and we see that the epidemic grows slower than before. And that's pretty intuitive because the infectables are being cleaned periodically, so the infection is essentially being passed on from people to people. The objects do not play a major role in it, as they did in the previous animation. After a while, the epidemic does peak and then starts to subside. People start recovering and then the epidemic ends. What's really interesting is when we look at the infection tree or the infection forest for this animation. When we look at it, we realize that it is a forest. There are more than one trees, but look at how few of them are there. This means that only a few people got infected from the objects. This tells us that cleaning the objects regularly can be a great help during an epidemic. We've looked at several animations, and the question is, how do we flatten the curve? These animations have made it clear for us that we flatten the curve by changing our behavior. We flatten the curve by acting socially responsibly. We flatten the curve by socially distancing ourselves. We flatten it by avoiding large gatherings and by disinfecting things regularly around us. Many people ask why epidemiologists cannot predict an epidemic precisely. And the reason is because there are so many variables. It depends on how we behave. And therefore, epidemiology, though a very important science, is not as exact as physics. You also must have noticed that in my animations, I've made several simplifying assumptions. For example, one assumption that I have made is once people have recovered, they cannot be infected again. So the green dots never turn their color back to gray. This is not strictly true for COVID-19. There have been reported cases where people have been infected multiple times by the coronavirus. These simplifying assumptions are a routine in science. Scientists typically start with a model which makes a lot of simplifying assumptions and then start introducing more and more complicated features which reflect real life situations. Making these animations requires doing heavy computations. However, you must have noticed that in our animations, we don't have too many numbers. And the reason is because, as Richard Hamming said, the purpose of computing is insight, not numbers. I hope that these animations have given you insights that have been known to epidemiologists for centuries, and that is how to deal with a pandemic. We act socially responsibly, we avoid large gatherings, we disinfect things around us. COVID-19 poses a great challenge for us all. We must act responsibly and protect others. However difficult things may get, we cannot give up our humanity and compassion. So take care of yourself, stay safe, protect others, break the chain of community transmission. Wash your hands often and remember to smile at people, even when you're wearing a mask. Good luck.